Okay, I guess we are now live on YouTube. So apparently I guess it's working. And then I'll just give like 1 or 2 minutes for people to log in, and then I'll just start. Thank you. Once again, thanks for accepting the invitation.
Sure, pleasure.
So it's now 5 hours, the time difference.
Right.
Still 5 hours.
So it's 3:30 here.
Yeah. So the daylight saving time probably ends by the end of the month or something like this.
I think very soon. This or next weekend we're gonna switch.
Okay.
So sometimes we have, I think when we switch, we don't switch simultaneously. We only have 4 hours for a few weeks. Sometimes.
Yeah, true. Yeah, okay, because I mean, here in Brazil, we somehow suspended daylight saving time. So
you don't have it anymore.
Yeah, since like 2 years ago. So probably we stay like, because you're absolutely right. So we stay 4 hours for probably 1 month and something. Then then we just have the usual 3 hours. But now it stays 4 because we suspended it. I mean, there's always this discussion because there's no actually much difference. So
I mean, in Europe, there's also discussion to abolish it again. And what's interesting is that the country that's mostly for not doing daylight saving time is France, and that it's the country that most wanted it in the beginning. So
I see. So somehow it's changing. Yeah, it's interesting. So okay. So good. I guess we can probably just start to present you. So I apologize. I speak in Portuguese for like 1 minute, and then I'll switch back to something. Bom dia, pessoal. Bom dia a todos. Bem-vindos a mais esse colóquio aqui no Instituto de Física de São Carlos. Hoje a gente tem o prazer de receber o professor Guido Burkard, lá da Universidade de Konstanz, na Alemanha. Tá? Eu vou chamar a atenção para vocês que, novamente, a gente vai transmitir pelo canal do Instituto no YouTube. Quem tiver pergunta, por favor, enviem pelo chat, né? E ao final da apresentação, eu passarei essas perguntas para o Guido. Se alguém estiver desconfortável com fazer a pergunta em inglês, pode fazer em português, que eu traduzo na melhor das minhas habilidades aqui para ele poder responder. Tá? Se alguém tiver uma pergunta também imediata no meio, pode mandar. Eu também posso parar a apresentação e perguntar a ele, tá bom? Mas, de novo, obrigado a todo mundo por ter vindo. Eu espero que vocês façam bastante perguntas. E agora eu vou trocar para o inglês para eu poder apresentar o Guido. So, good morning, everyone. So, thanks for showing up for this colloquium at the Instituto de Física de São Carlos. So, it's really a pleasure to have Guido Burkard here today with us. So, Guido did his undergrad studies in ETH in Zurich, Switzerland. Then he did his PhD in Basel, also in Switzerland. Then he moved to the US, to New York, to do a postdoc at the IBM. So I guess he spent like 3 years there. And then he came back to Switzerland to a faculty position, also in Basel. So he stayed there for a couple of years. Then he moved to Germany, to Aachen. And then finally he moved to Konstanz, where he has been since 2008, I guess. And he just informed us he's now head of the department there. So I mean, he's been there for a while. So his main research interest is it's mainly in this interface between condensed matter theory and quantum information. So I guess he's going to talk a bit about this today to us. So mainly he has several interests, so I'll just cite a couple of them. So theory of solid state quantum information processing, quantum error correction, and solid state source of entanglement photons and electrons, which I guess matches the topic of the talk today, and also graphene and 2D materials. I mean, he has a broad spectrum of interest. So I guess we hear lots of interesting stuff today. So Guido, thank you so much for accepting the invitation. Please.
Thank you very much, Eric, for the kind introduction and for the invitation to speak here online to the Institute of Physics in São Carlos. It's a great pleasure. Thanks a lot for the invitation. It's really nice to see some of you whom I know, whom I've known for a long time, and to present some of the things that I'm interested in this audience. So that's really a great pleasure. Also, if you have questions, I'll be happy to answer any questions you have either during the talk or after the talk. So I'd like to tell you about quantum computing and cavity QED with spins in condensed matter systems. And I'm gonna try to introduce the topic so that if you haven't heard about this before, it should be, if I do a good job, then you should understand something about it. Okay, so maybe as a first step, I should probably bring you up to speed or update you in terms of what's happening in quantum computing. Probably this is unnecessary for some of the people whom I know in the audience, but I'll do it anyway for people who are not so familiar with this topic. So what's happening in quantum computing? Maybe some of you have heard that last year something happened. There was a new result reported by a team at Google, and they claim that they have reached what they call quantum supremacy using a superconducting quantum computer. And you see here, this was in Nature last year. Fairly long list of authors, group headed by John Martinez. So, this is the chip that they have built. It's actually, this is a centimeter across, and it's a superconducting system. It works at low temperature. And, as a university physicist, it's kind of amazing to me how big this group is. But actually, if you ask, here's the CEO of Google, just standing next to the machine where the experiment was done in. This is a cryostat, so this is what they use to cool the system to sub-Kelvin temperatures. And if you ask him about the size of this team, he says, well, this is a relatively small team for Google. So I think if they want to, they can probably do even, work even harder on this topic. So it's not, for them, it's not so impressive. What I would like to do first is to kind of give you an idea of what it is that they're trying to do with this quantum machine. And just as an example, I choose a sort of the standard or one of the earliest examples where we know that quantum computers could do something that classical computers are basically not able to solve a problem. And this is the famous algorithm by Peter Shor from almost 25 years ago. And what it does, or what it can do, is it can factorize a large number, a large integer, like the one shown here, into its prime factor. So that's what you want. And it's known that this problem is very hard for classical computers as the numbers that you want to factor are becoming larger. And so what the quantum computer is doing, or what you're doing to solve this problem on a quantum computer, is you encode the problem into a quantum state. So it's a wave function that describes the state of the system. And then this is fed into the machine that performs a quantum time evolution. This is described in quantum theory by a unitary operator, and I'm calling it U, and it's just a big box at the moment. And what comes out is, a new state, the new state, the final state of the system. And then you do a quantum measurement, and if you do the thing right, then what comes out is, for instance, one of these factors. So that's the idea. And if you think of it, if I give you such a complicated unitary, so that's essentially what Shor did. He found this unitary, or maybe he did a bit more. But so basically, if you're given this unitary and you're supposed to build a machine that performs this unitary, it's actually a very hard problem. I mean, you have to come up with a controlled Hamiltonian, a system that has certain parameters, certain interactions, and of course the quantum information has to be represented in certain quantum systems that interact in a certain way described by this Hamiltonian that you control from the outside so that it performs this time-dependent dynamics. And then in the end, this unitary comes out. This is a very complicated control problem. So this would be very hard to do. So what we can do instead, and this makes life really much simpler, is we can split up this computation into smaller elementary logical operations called quantum gates. And this is really it's the same idea you also use in classical computation, that complicated functions that are computed are basically can be assembled from smaller units, from smaller logical operations that act on only 1 or 2 bits. And this is the same we're doing here in quantum computation. So let's look at this description of the program, the quantum program. And this description here is called the quantum circuit. It's, if you're a physicist, you can think of it as a space-time diagram where on the vertical axis you have space. Basically, you have discrete units, these lines, these are the quantum bits or qubits. There are two quantum two-state systems that can be in 0 and 1, and also in quantum superpositions of 0 and 1. And on the horizontal axis is time. So this diagram basically describes what happens to the qubit during the computation. So these are the qubits, and then there can be these unitary quantum gates, these elementary operations that can act either on a single quantum bit, then they're called 1-qubit gates, or they can also combine 2 qubits, and then they're called 2-qubit gates. And that's all you need. So there's a statement called universality, which says that an arbitrary quantum computation can in principle be built from these elementary operations. So if you have a system which can perform these elementary operations, then in principle you can build a quantum computer. This is already an old result. It's even older than the Shor algorithm, and that's of course very, very important. So let me, because I'm going to talk about this a few times now in this presentation, let me give you let me describe to you what this elementary 2-qubit gate looks like, the so-called control not operation that we need to implement a quantum computer. So we have 2 qubits, a control qubit C and a target qubit T. And then there's an operation that basically what it does, it flips the target qubit if the control qubit is in the 1 state. So the qubits can be in the 0 or 1 state. If the control qubit is in the 0 state, nothing happens to the target qubit. So, you know, the output is equal to the input. But if the control qubit is in the 1 state, as shown here, then the target qubit will be flipped. So it's going to be 1 if it was 0 and vice versa. Now it's interesting. So so far this was all classical. So this is what you could also do with a classical computer. However, a quantum bit can also take a value that's a superposition of, let's say, 0 and 1. So it's a quantum superposition of 0 and 1. And if you input a superposition, then what you get is the corresponding superposition of the outputs that you would get for 0, 0, and 1, 0. So you get a superposition here of the target qubit being unchanged if the control is 0, and the target qubit being flipped, that is 1 in this case, if the control was 1. And this superposition then, I mean, I cannot write this anymore as the state of the first qubit and the state of the second qubit. It's really a state where the first and the second qubit now become very strongly correlated. If the first qubit is 0, then the second is also 0. And if the first one is 1, then the second is also 1. And actually, this is even, turns out this is even stronger than the classical correlation. And this kind of correlation we call quantum entanglement. So now if you, I don't know, if you, probably most of you know this notion and they know what entanglement is. If you don't know what entanglement is, this is exactly what it is. It means that a state of a system consisting of 2 parts cannot be represented as the state of the first part of the system and the state of the second part. They're really correlated in this way. Also, if you are if you have just become a parent to a new child, and if you want to tell your child immediately what this is, this very concept that maybe will be normal in a few years that kids learn in school, so then you can buy a book, Quantum Entanglement for Babies. So maybe in the future, I don't have to explain this anymore. So maybe just to wrap up this introduction, I'd like to give you a little summary of my view, what Google actually achieved. The Google experiment implemented a processor which consists of about 50 functioning superconducting qubits. They're depicted here in these crosses are qubits. The blue ones are couplers. Actually, those are also qubits, but they're used as couplers. And they're arranged in this architecture. And they run quantum algorithms that are depicted here in this quantum circuit, just like the one that I showed you before. And you can basically choose an arbitrary program and run it on this computer. So it's really a universal quantum computer. So it's unlike other computers that you can already buy, like D-Wave, that is not a universal quantum computer. And now you can ask, how good is this computer? And a figure of merit is the gate fidelity. So that's basically the probability that a single quantum gate produces the correct result. And this fidelity is greater than 99% in this case. So the probability that if you perform a single elementary logic operation on this machine, the probability for an error to happen is about 1%. Maybe that sounds good for physicists, but if you're a computer scientist, you will notice that this is terrible. I mean, it's for a classical computer, this would be terrible if every gate would have an error of 1%, because I mean, these errors accumulate exponentially, and after a few operations, actually your computer would completely, give random results. And that it turns out that the length of a program that you can run here on this machine is only about maybe 20 to 40 steps long, and then basically the outcome is completely random. But at least, I mean, this is the best you can do nowadays. And indeed, it's so good that they can show, or they claim that they can run certain computations on this machine that are practically impossible with the best classical supercomputers, and that's what they call quantum supremacy. Google says they ran a computation that took 200 seconds on this quantum computer that would take the fastest classical computer about 10,000 years. Then IBM came in and said, well, we built this best classical computer. And if you use it cleverly, you can do it in 2.5 years. No matter what, I think still the achievement that Google did here is really remarkable. And it shows really the power of quantum computation. One should also say, though, that what they do here is really a proof of principle. It's not a useful quantum computation. What they're running here is, so they're not really solving any problem. They're just picking random programs. They're running them. They're performing a statistics. And from the statistics, they can distinguish classical computation from quantum computation. And another point that I would like to make also in view of what comes afterwards in my talk is this machine is really huge. I mean, these qubits, so every single unit here is about 0.5 millimeter. So this is for the experts, this is a superconducting qubit plus a resonator. The superconducting resonator is part of the qubit. So these qubits are really big. And so that's why a 50 qubit machine is already 1 centimeter chip. And you may wonder, how big this machine will become if you want to make thousands or even 1 million qubits. This machine would become very, very big. And so what I'm going to talk about here is a different implementation of quantum computing, also in solid state. And actually, so it's also working. I would also make the point that this is also a working universal quantum computer. It's not based on superconducting systems, but on electron spins in semiconductor nanostructures. To be more precise, it's in silicon and based on quantum dots. And these are really nanoscale objects. So I would argue that in principle, these are more scalable than the machine we've seen before. Or at least, well, I mean, I would say that the obvious scaling problem that we've just seen is not as obvious here. This universal quantum computer was also demonstrated. In fact, it was demonstrated before the Google machine. And now maybe some of you are wondering, why didn't I hear about it? Maybe the reason is that it only has 2 qubits. So that's the big difference, that in this scaling, we are not at the point where the superconducting qubits are. We are really at the very beginning, where we can do everything that's necessary on 2 qubits, because as you know by now, that all we have to demonstrate is 1 and 2 qubit gates, and this has been demonstrated in one and the same device, and so that has been done 2 years ago. And what basically we have to do now is to make this better and to scale up. So also, okay, to be completely honest, one should also say in the first experiments, the gate fidelity was really lousy, only 80%. It was enough to show the proof of principle, but this fidelity has already been increased later. Last year, actually, there was a demonstration from an Australian group which showed 98% fidelity of the 2 qubit gate. Maybe another thing that's interesting, if you're wondering, should I work on spin qubits or superconducting qubits? The person who has headed the Google experiment, John Martinez, is actually not with Google anymore. He actually joined a spin qubit effort in Australia. So here you see John Martinez talking to Michelle Simmons, who is heading the spin qubit effort, or one of the spin qubits efforts in Sydney, Australia. It's quite interesting. Okay, so let me give you a brief outline of the remainder of my talk. I'm going to give you now a brief introduction into spin qubits from the point of view of a theorist. And then I'll talk you through a few problems that one has to solve in order to implement these spin qubits. And they're interesting physics problems. And some of them have been solved more or less, and some of them are still basically challenging us today. So the first one is nuclear spins, that has to do with materials. The second one is electric control of spin. And then that will be enough to actually understand how the universal 2-qubit processor works that I've just mentioned. And then I'd also like to talk to you about long distance coupling between qubits, and that will lead us to cavity QED with spins. All right, let me give you a few informations about spin qubits. Maybe it's also a good idea now to show you what other things there are. I mean, there is a number of systems in which people are trying to implement qubits, and I've tried to group them here in either atomic systems or solid state systems, and then also divide them into spin systems and other systems. And so basically, on the atomic side, the most prominent one nowadays is trapped ions. Actually, what's mostly used in these systems is some spin degree of freedom of these atoms. That's one area. And then there are the superconducting circuits. Arguably, they have the biggest quantum computers at the moment in terms of the number of qubits. And then there are the spins in solids, and that's my topic. And there are different systems where these spins can be controlled individually and in a coherent way. One is these quantum dots, nanostructures that are manufactured in semiconductor structures. And another area is defect spins that are naturally occurring in wide bandgap semiconductors such as diamond or silicon carbide. So I'm going to be talking here about these solid state systems, and maybe you can also ask, we've already heard about Google and IBM, and several companies are investing mostly in solid state quantum computing. And for instance, on the spin side, Intel is active, and then on the superconducting side, Google and IBM are active. And then, for instance, Microsoft is taking a different approach. They're actually combining superconducting and semiconducting systems to make very exotic topological systems. I'm going to also talk about combinations of semiconducting and superconducting systems, but in a different sense, where we're trying to do cavity QED. So the system I'm interested in is are systems where the qubit is stored in the spin 1/2 of a single electron. And basically, the logical mapping is very simple because the electron has a spin 1/2. It has two distinguishable states, let's say spin up relative to a certain quantization axis and the spin down relative to the same quantization axis, and I just label these states 0 and 1, and those are my computational states of the qubit. And so these electron spins can then be localized in semiconductor quantum dots to address them individually, or they can also be localized in defects. And one advantage of using spin rather than charge degrees of freedom, position degree of freedom, is that this degree of freedom is really quite robust against charge noise, because the spin doesn't directly couple to electric fields. I mean, there are systems nowadays with, for instance, in the group of Segu Tarucha, there was a demonstration already 4 years ago where up to 5 dots filled with a single spin each were controlled individually. Also, every spin was controlled individually. Here's a picture from the group of Jason Petta at Princeton with 9 quantum dots that carry spin qubits. So these, what you see here is an electron micrograph, a top-down micrograph of a silicon-silicon germanium heterostructure, and these red and blue features are metallic electrodes, and I think so. One of them is depletion, and one of them is accumulation. So you first accumulate electrons. I think it's with the red gates, and then you deplete part of them again to make really zero-dimensional structures. So underneath these, or between these green gates, you have 1, 2, 3, 4, 5, 6, 7, 8, 9 quantum dots, each carrying a single electron. And then there are 3 more quantum dots down here, and they're used to measure the state of the spin of each of these quantum dots. So this is a 9-qubit register. There are different, as I mentioned, there are different kinds of spin qubits. We can have electron spins in semiconductor quantum dots. One can also use the nuclear spin of donor atoms, for instance. One can, instead of using the spin of the electron, one can use the spin of holes in semiconductors, and in some way, and in some ways, in an even more coherent way. One can also use defect spins in diamond or silicon carbide, and one can also use spins in 2D semiconductor quantum dots. So 2D semiconductors would, for instance, be transition metal dichalcogenides, really sort of materials in the sense of similar to graphene, where that have a band gap and where quantum dots can be fabricated. For the sake of brevity, I will stick to the 3D semiconductor quantum dots for this talk. But these are all areas that where more or less this activity also exists. So let me just give you an idea what such a quantum dot qubit array would look like and how we would describe it theoretically. So basically you have your 2D electron system, you have metallic gates that deplete the electron gas, and the remaining electrons are only in this somewhat middle shade blue ovals here, and these are the quantum dots, and you can actually tune the electrodes, the voltages on the electrodes in such a way that you create a potential that contains, let's say, only a single electron in each dot, and the spin of these electrons is our qubit. And then you can also tune the center electrodes between the qubits in order to tune the exchange coupling, which is is described by this first term here, which couples 2 spins and which is generated by virtual hopping of electrons from one dot to the other. I'm going to say a few words more about this. Another thing and so basically this exchange coupling is what can be used to generate the 2-qubit gates, let's say between the qubit 1 and 2 here. This was demonstrated already quite a few years ago, and it has been continually improved over the years. And then the single qubit gates, for that you would need to address a single spin. And I told you before that these spins do not really talk to electric fields directly. So you would have to use a local magnetic field, Bi here, that basically is applied to one of these spins. And that gives you the possibility to rotate single spins, which corresponds to the 1-qubit gates. The state of the art of these 2-qubit gates, as I mentioned, is that these can be performed with a success probability of about 98% or better. And the 1-qubit gates are even better. I think one of the best demonstrations is from the group of Seigo Tarucha at Tokyo, and it's already better than 99.9% success probability. And so in principle, as I claimed before, these two ingredients are sufficient to perform arbitrary quantum computations. But I mean, I'm saying in principle for a reason. I mean, first of all, you have to implement them in the same device, and also there are many things that that actually can go wrong. And so here's what could go wrong. One thing that can go wrong is that even though you may have depleted the electron system here completely, except for these very well-controlled single electrons, actually in most solids, you have other spins around, and those are the spins of the atomic nuclei of the system. And these have spins, and these spins to your electron spins via the hyperfine coupling. And they will actually decohere your system. Your decoherence time of the electron spin T2 will be used by quite a bit because of this coupling. And so this is in some sense a materials problem. And so let's see what can be done. I mean, actually, this was realized quite early on in this field. And so people have been working quite hard to improve the situation here, starting out with gallium arsenide, where we have, let's say here, 1 electron spin qubit talking to 1 million nuclear spins in a typical quantum dot with a inhomogeneous decoherence time, phase coherence time of only around 10 nanoseconds, really limited by these nuclear spins. This has been improved. And well, okay, I try to liken that to, you know, kind of the way people name epochs in human history or prehistory by the materials they're using. So I would call this the Stone Age of spin-based quantum computing. And now you can ask, you know, what is the Bronze Age? Well, that's sort of where we're in at the moment. Basically, people have switched materials now using silicon, and silicon has a most abundant isotope that has no nuclear spin. So you only have about 5% of all the atoms in the material that carry a spin. And that has increased the coherence time by about a factor of 100. So these electron spin qubits are much more coherent since we have silicon available. And okay, now you can ask, what is iron? Well, the next thing you can do, and people are already doing this, is you can take the remaining silicon, the remaining atoms that have a nuclear spin out. So in the case of silicon, this is silicon-29, and you can basically isotopically purify your material and try to make pure silicon-28. And if you do that, then you get a reasonable purity. You can gain another factor of 100 in coherence time. And so these coherence times are really very long already. And they're definitely competitive with the superconducting qubit coherence times. You can go even further and put back some individual nuclear spins have very long coherence times as well. You can also, I mean, you can ask, you know, is silicon the only option? And I think it's, in principle, it's not, but it's a very good option. If you look at the periodic table, and this is taken from Ed Laird. So if you also indicate here the fraction of naturally occurring nuclear spin-free isotopes, then basically you see which materials might work. So the 3,5 materials are not so good here because all the stable isotopes of these materials have a nuclear spin, and so there's 0% spin-free atoms in these materials, and you cannot change that really. However, in the group 4 elements, there are many possibilities. Silicon is one, so we have 95% silicon-28 already in natural silicon. And for carbon, it's even better. Carbon-12 has 0 spin. And so these are, in some sense, favorable materials for spin qubits. And so in carbon, people are using, of course, a diamond as a basis for defect spins that are very coherent, and that's one of the reasons. You can think of using graphene or carbon nanotubes. And I've already mentioned silicon. There's also a combination of silicon and carbon in the form of silicon carbide, a material that's a bit similar to diamond, but with a smaller band gap. And the defects in this material are currently studied in a European network that tries to use them as a spin photon interface, so as a spin qubit memory that can also coherently emit photons for quantum communication. And then there are also these other materials. Some of the transition metals and the chalcogens also have favorable nuclear spin properties, so that in principle the 2D semiconductors that are built from these materials, the transition metal dichalcogenides, they're also very interesting materials for spin-based quantum computing. Just to mention briefly, there are also some difficulties if you use these materials, these group 4 materials. Most of them have a property called Wally degeneracy, which simply means that in the solid that is built from them, or in most of the solids that are built from them, the conduction band has a multiple minima. And so basically, if you have electrons in silicon, it means that they can be in, even if they're in an orbital ground state of such a quantum dot, they can have, in addition to having 2 possible spin orientations, they can have 2 possible Wally states. And so this leads to the fact that instead of a qubit, you get sort of 2 qubits, spin and Wally. And if you couple them in adjacent quantum dots, instead of this simple exchange Hamiltonian, you get something more complicated, which could be interesting, but also it is also more complicated. And what we're usually doing when we work with silicon is to try to get rid of the Wally degree of freedom by splitting off the Wally excited states by an energy which is as large as possible. We have solved the materials problem. We're in silicon. Everything is nice and coherent. Now, what else is difficult? Another thing is that you need to control individual electrons, electron spins, and the spins don't immediately talk to electric fields. But electric fields is really what you can control very well here with these metallic gate electrodes. Magnetic fields is much harder, and in particular on a small length scale, it's very hard to control magnetic fields. So the second problem is electric control of spin. I only have one slide on this. So basically, you know how to control spins with B fields, with magnetic fields. You can apply a static field and then apply an oscillatory field perpendicular to it. And if you do that, you will perform electron spin resonance. And so that's a way to rotate the spin, so to perform a certain logical operation, let's say the 0 to 1 flip. But with the electric field, it's not so easy. You have to somehow couple the spin to the electric field. So, and that works by coupling the spin to the spin of the electron to the motion of the electron. And this can be done with spin-orbit coupling. But actually in silicon, spin-orbit coupling is fairly weak. There are other tricks. Actually, what we're using at the moment is as kind of synthetic version of spin-orbit coupling, which is induced by an external B field gradient. And this is, by the way, how these 99.9% single qubit gates were achieved. And so the way this works is the following. You have your localized electron with a spin, and you use an electric field, a microwave field, an oscillatory field, to basically shake the electron in its potential well. And then you also place a small micromagnet on top of the structure, which produces a magnetic field gradient. So the stray field of this micromagnet is not homogeneous. And if the electron sloshes back and forth in this inhomogeneous magnetic field, what the electron effectively sees in its rest frame is an oscillating magnetic field. And then this basically does the same as the usual electron spin resonance field. There's a sort of improved version of that we've been using the last few years, which is called flopping mode EDSR. So EDSR is for electric dipole spin resonance. It's just rotating spins with the electric field. And we're using here a double quantum dot. so two quantum dots that are tunnel coupled, filled with a single electron. So the electron can be on the left or on the right. And if the double dot is in the symmetric configuration, the electron can go back and forth. And so the electron can move over a long distance, and therefore it's basically it constitutes a very good antenna. And it sort of also, it basically probes a large spatial volume that contains a large, a large gradient, large field difference in this gradient field. And so that's basically the workhorse of the experiments that have been done at Princeton and theory that we've been doing along these lines in the last few years. So this now basically brings me to the two-qubit processor. The only missing ingredient for that is the two-qubit gate, how it actually works. So the exchange coupling is based on the Pauli exclusion principle. So simply means that if you have two nearby quantum dots that can hold an electron, so basically have a single orbital that can be occupied by an electron. If you have two quantum dots that hold an electron that both have spin up, then this left electron cannot hop onto the right quantum dot because of the exclusion principle. This state cannot be occupied by two spins, by two electrons with the same spin. And so if the two electrons have opposite spins, this hopping is possible. And actually this hopping, this virtual hopping, leads to a reduction of the energy of the two-qubit state by approximately t squared over u, where t is the hopping matrix element and u is the on-site Coulomb repulsion energy. And so this energy difference is now really an energy difference between two different spin states, namely the spin triplet and the spin singlet. And this energy difference is what's called the exchange energy. And you can write the exchange Hamiltonian as basically this exchange energy times the projection operator on the spin singlet state. And if you can rewrite this in terms of spin operators. So it's basically the singlet is basically the state with spin 0, and you can write it like this, and then you can express it in terms of spin operators. And what comes out is really basically the operator for spin 1 times the operator for spin 2. And so this is basically the Heisenberg spin Hamiltonian, and that is known. We know that this can produce a universal quantum gate. And so the way this works is that you switch this on for a certain time. So you have this Hamiltonian, and now it comes this control problem, but only for 2 qubits. You basically solve this exponential, and it's actually easy to calculate because this is a projection operator. You can sum up this exponential series here. This is what comes out. And now this phase phi here is given by the integral over the exchange coupling as over time. And so if you pulse the exchange coupling such that this area under this pulse is, let's say, pi, what will happen is that you get pi here, and so e to the I pi is -1, and to get 1 minus the projector on the singlet. And so what actually that does is that it swaps the states of the two spin qubits. So if you put spin up into dot number 1, put spin down into dot number 2, and you perform this pi pulse, what comes out is the spin down in dot number 1 and spin up in dot number 2. So that's useful because it allows you to move around the qubits, but it's not a universal quantum gate. This is not sufficient for quantum computation. What you have to do for quantum computation is to do this pulse, which is only a pi half pulse. So you kind of have to start swapping, but then stop halfway. And what comes out if you do that is you get a superposition of the initial state and the swapped state. And so that's another example of an entangled state. So this is another gate that can produce entanglement. We call it square root of swap. It's not the same as C0, but it can be used to produce this controlled knot. So once you have this, and in addition, single qubit operations, you can do everything. And so this is in some sense all you need. And this you can do even if you also apply a homogeneous magnetic field, because the homogeneous magnetic field couples to the total spin, and that commutes with this Hamiltonian. And so that's how you can do quantum computing actually quite fast. It turns out that actually the fidelity here is limited by charge noise, and you have to do this C0 gate sequence. Maybe that's something that is a bit tedious, but it can be done. Another way of doing things is to work in a gradient magnetic field. And actually, maybe you remember that we want to work in a gradient field anyway, because we want to use it to electrically control the spins. And so you can also do directly a universal 2-qubit gate directly in a gradient field. These gates are a bit slower, but on the other hand, they're robust against charge noise. And so that's basically the idea of the gate. And I'm going to show you here, and I'm going to show you how it works here. So basically, this is the system. You have two quantum dots that are controlled by these three electrodes, left, middle, and right. You have one electron in each quantum dot. And so you also have a gradient field. And so the gradient field has two functions. First of all, the Z component of the gradient field, so that's the component that's along the externally applied field, that distinguishes the resonance frequency of the left and right spin for electron spin resonance. The resonance frequency is given by the level splitting of spin up and spin down. And so these gradient component will allow you to selectively address either the left or the right electron spin. The other component of the gradient is in the perpendicular direction, and actually this creates this artificial spin-orbit coupling that allows us to rotate the spin by shaking the electron using one of these gate electrodes. And we select, for instance, the left electrode to rotate the left spin. And then there's also the middle gate, and that just controls the strength of this exchange coupling that we use to do 2-qubit gates. So this is a simple level diagram that you get. I mean, these are two spins, 1/2. There are 4 states: down, down, up, up. And in an external magnetic field, these are split by the Zeeman interaction. So up has the highest energy, down has the lowest energy. And then here in between is the Zeeman splitting. And up, down, and down, up have the same energy. Now, if you apply a magnetic field gradient, these up, down, and down, up states will split up. So that's what allows you to distinguish the resonance frequencies of the left and the right electron spin for EDSR, for single qubit gates. But it's not enough to do a 2-qubit gate. For a 2-qubit gate, you also, for a 2-qubit gate, you also need to switch on the coupling between the two spins. And then actually there's a certain frequency which will rotate, let's say, the left spin only if the right spin is up. And so if you think of it, if you pulse this is exactly a C0 gate. So if you identify spin up with 1 and spin down with 0, this basically rotates. And so basically the first qubit here, the left spin is the target and the right spin is the control. So this basically rotates the target if the control is 1. And this is a C0. And this is a system where this was realized. This is from the group of Jason Petta at Princeton. And then, I mean, in theory, we can calculate what we would expect. For instance, what is the probability of spin up of the target? This is the red curve as a function of time for different input states. And then we can look at the experiment, and we see basically they agree. You can also read off the gate time. So basically the C0 gate takes about 130 nanoseconds. You also see that the real 2-qubit gate is not perfect. The readout visibility is not 100%. So this probability doesn't go between 0 and 1, but between something like 0.15 and 0.8. And so this visibility is not perfect. And this is basically how you see that the fidelity of this gate is not 100%. There are other effects that I can briefly mention. For instance, if you drive this resonantly, then you will actually also drive the other transitions non-resonantly. So this will lead to lower amplitude but fast Rabi oscillations if you're in another state. And so these are if you look on the Bloch sphere of the target qubit, the resonant target qubit, so this is basically what you see here. This is basically a great circle around the Bloch sphere, but these off-resonant processes are smaller circles. And this can be, actually this problem can be solved. You can just make sure that you make an integer multiple of these off-resonant trajectories while you're doing exactly 1 pi pulse on the resonant side. So now I think I guess I don't have too much time left, but maybe I'll say a few words about what's going on now with long distance gates and cavity QED. I mean, there's one remaining problem that I haven't talked about yet, which is if you look at these circuits and I said, okay, if you can do these 1 and 2 qubit gates, then you can do everything. That's true, but actually for the 2 qubit gates, you should look closely. The 2 qubit gates should connect any pair of qubits, not only nearest neighbor qubits. Whereas this exchange interaction, maybe you remember this, this is based on nearest neighbor electron hopping. So this is a very local interaction that only works between nearest neighbor electrons. And so this is not going to work. So you have to find a solution how to couple remote qubits. And one idea is to use superconducting resonators that already couple remote qubits in remote superconducting qubits and combine them with the semiconductor spin qubits with their long coherence time. So this is something we've been very interested in the last few years. And maybe I think I have to go a bit more quickly. So the model we're using ultimately is this Jaynes-Cummings model, which simply describes a 2-level system that could be an atom, or in our case, it's an electron spin. It's described by this Pauli operator, and a single mode of an electromagnetic resonator. This could be an optical cavity with mirrors. In our case, it's a microwave cavity. And so it's just a single mode of the quantized electromagnetic field. It's just described by a harmonic oscillator. And then the two couple via the electric dipole interaction, and the coupling strength is given by the product of the electric dipole, and this scales basically with the size of the 2-level system of the atom times the electric field in vacuum. So this is basically the electric field of a single photon. And this scales inversely proportionally with the square root of the volume of the cavity. And then there are also dissipative effects like the decays in the 2-level system, spin decoherence in our case, and photon loss from the cavity. And we would like to have a situation where the coupling is stronger than both of these effects. And then we say we're in the strong coupling regime. And this is actually when quantum information can be exchanged several times between such a 2-level system and the photon in the cavity. And so that's the regime where you can imagine that, let's say, 1 qubit gives off the quantum information to the cavity, and then another qubit receives it coherently at another place in the cavity. And so that's the regime we want to be in. So as I said, this depends a lot on the size of the 2-level systems. If you use real atoms, let's say hydrogen atom, this is very small, and this coupling will be very, very, very small. You can use atoms in an excited state, in a highly excited state, such that the electric dipole becomes larger because the size of the system becomes larger. These are the so-called Rydberg atoms, and that's how the first cavity QED in atomic systems have been done in the 1980s and 1990s. And you get a few megahertz with typical microwave cavities. Actually, we get similar sizes for quantum dots in semiconductors. And we get therefore similar coupling strengths. We can do a little more tricks, maybe other tricks than in atomic systems. For instance, we can double these systems and use in this flopping mode qubit, we can use a double quantum dot and immediately double the size. And we can also control the electric dipole with just switch it on and off electrically. Of course, in the superconducting qubit business, they can make even larger systems that have even larger couplings to the cavity. So in our case, this is an example from 3 years ago. Here's a superconducting resonator on a chip. This is a very large system. These lines here are aluminum superconducting lines, and then basically here are the terminations. And so this is a microwave resonator, a coplanar microwave resonator. And then in this red box here, is a double quantum dot. This is much, much smaller. And so this is a hybrid semiconductor superconductor system where one of these gates now really couples to one of the electrodes of the resonator. And if you basically just probe the resonator, you can probe microwave transmission here. This is microwave transmission as a function of frequency, just shining microwave through. What you see is just the resonance frequency of the microwave, and the width here is giving you the quality factor, the photon loss rate. And then you can put a double quantum dot in it. Maybe I cannot show the details here. What you will find is, you get a signal from the resonator here. That's basically this vertical line, and then you have basically used the double dot tuning parameter epsilon to tune your double dot into resonance with the resonator. And as you do so here's the qubit energy, and as the qubit energy becomes resonant, the two couple, and then basically you get a hybridization of the cavity mode with the sort of this one electron plasmonic mode, if you wish, and you get this splitting here. And if you're in the strong coupling regime, you can actually resolve this splitting. The theory we're using to calculate these things is input-output theory. It's known from quantum optics. So basically, we solve the quantum Langevin equations, and therefore we can actually fairly well understand these kind of signals. And now we couple the spin, and then maybe I'll just, so to wrap up, just show you how we do this. So what we use is this flopping mode system where you have a double dot. So you have a spin 1/2 in a double quantum dot and a gradient field. And as the double dot, as the electron goes back and forth, now it couples to the quantized field of the cavity, and the quantized field via the magnetic field gradient also couples to the spin. So it's kind of a artificial spin orbit coupling that allows us to couple the spin to this cavity mode. And this has been realized by 3 experiments shown here. And there's a 4th experiment using a different type of qubit from ETH here. And so the theory basically just takes into account the spin degree of freedom in a cavity. And so then basically what we find is that the spin to cavity coupling is proportional to the charge to cavity coupling times the magnetic field gradient. And then it depends on the resonance between the qubit splitting and the Zeeman splitting, how big the coupling will be. And what we find, actually this is an interesting interplay between the strength of the coupling and the strength of the decoherence, because the spin qubit actually gets worse as you couple it to the charge, because it becomes vulnerable now to charge noise. But because there's a square here, because this goes with the square of this factor, you can increase the coupling by a bigger factor than you increase the decoherence. So in the end, okay, so we can now also model this. You see this avoided crossing in the transmission. Now is a signature of spin to cavity coupling. And so it is in the strong coupling regime. And one can now, as a function of this detuning, this is now controlled by the interdot tunnel coupling. You can see that you can make the coupling very strong, but at the same time, you make the decoherence of the qubit, of the spin qubit, very, very strong. And but you can work here on this side where the coupling is already getting bigger and the decoherence is not that strong yet. So basically you can be here, for instance, where the coupling is, let's say, maybe 8 megahertz and the decoherence is only 4 megahertz. And you can also beat the cavity loss rate. And so that's why you can enter the strong coupling regime. And so this is, I think, my last slide. Maybe looking forward, what we're trying to do is now to use this for cavity-mediated 2-qubit gates, where you have 2 such flopping mode qubits coupled to the same resonator mode. This will, we know already, this will mediate a long-range interaction. And we can make gates, and we can calculate its fidelity, and we can optimize it. We're not there yet. The coupling is not big enough yet, and so we're trying to find ways to increase this coupling and to combat the decoherence effects. And so that's really work in progress at the moment. So with this, I think I've talked for long enough. I'd like to wrap up. What I've shown you is this local controlled NOT gate in a B-field gradient, which is you can view as a universal 2-qubit quantum computer. And what we need to do there is to increase the fidelity of the gates, in particular the 2-qubit gate. We've reached the, our experimental colleagues have reached a single spin photon strong coupling regime, which one can use now for quantum gates, also for readout, and also for protecting the qubits. And we're trying to go towards cavity-mediated gates and readout. If you're interested, here's a very recent review article, mostly on cavity QED. And I should also acknowledge my collaborators, the theory team in Konstanz, former and current members, and also the experimental colleagues at Princeton and also at NIST in Maryland. So thank you very much for your attention. Sorry for going perhaps a bit over time, and I'd be happy to reply to any questions you may have. Thank you very much.
Thank you. Thank you very much, Guido, for this very nice talk. I guess the time was perfect, actually. So thank you so much for this very broad overview and also overview of your nice work you've been doing recently. So I myself have a couple of questions. I guess people also have a couple of questions. So they're sending them through the chat. So I'll start with one mine. So first, just a kind of curiosity, actually, when you start discussing this quantum supremacy business, you said essentially that the IBM was different from the D-wave quantum computing. And what is actually this difference? I mean, what you said that one is programmable and the other one is not programmable. Mm-hmm. So what does that actually mean?
So what I mean is, I should go to this slide. What I mean is that basically in the IBM computer, this program, you can choose arbitrary sequences of gates. You can program it. I mean, actually, you can do it. There's a programming language called Qiskit. You can try it. I mean, it's, because this computer, not this one, but there's an IBM one that is in the cloud, and you can basically program it, and you can run any quantum program you want, as long as it's not too long and it doesn't have too many qubits. But in principle, it's arbitrary. And the D-wave, it's basically what it does. I mean, it has a hardwired, or more or less hardwired Hamiltonian. So I would say it's more like the Hamiltonian. You can to some extent you can parameterize the Hamiltonian. You can change the parameters in the Hamiltonian, and then you can run this adiabatic change. You start from an initial Hamiltonian and some initial state, and then you slowly change the Hamiltonian, and then you get a final state. So, but that doesn't correspond to an arbitrary quantum program. So I think it's a very different mode of computation. It's really, first of all, you change a Hamiltonian, and it's not the unitary that you define, and also I think it's not arbitrary. It's really quite restricted.
Okay, thanks for the clarification. So I have a question from Federico, from Fred. He's asking that there's a recent paper from Google reporting a Hartree-Fock simulation where several layers of error corrections were applied to reach a reliable computation. And he's asking if you could talk about error correction in your platform and how does you think this will show up in your device? Yeah, so I mean, that's a good point. I think we are still quite, I mean, this recent result, I mean, I guess maybe that's sort of the state of the art in terms of error correction. I think for most available hardware, I think error correction is still not really possible, or only sort of in a very restricted sense, because quantum error correction usually uses a lot of qubits, and so these number of qubits are usually not enough to do full error correction. I think one can sometimes do limited error correction, but of course in the spin-based quantum computer, we are even further away from that. I mean, we have to scale up
even more before we even reach these 50 qubits. And at the moment, I think it's a bit too early to think about error correction. But in principle, once we have the same number of qubits, of course, in some sense, the error correction works in exactly the same way, because we're also talking about universal quantum computing. I'm not sure I answered really the question, but I think for us at the moment, it's a bit too early to think about error correction in these systems. I mean, it's good to think about error correction, but we cannot really implement it yet.
Okay, thanks. So I have a curiosity. When you start about talking your qubits and your quantum dots with spins, so first you said that your, let's say, the spin-spin interaction with just restrict to nearest neighbors. So first I'd like you to comment, I mean, how are you sure that's just nearest neighbors? And then, I mean, the last part of your talk, you said, oh, I'd like to go to have this coupling, this spin exchange to be long ranged. So, but and then I have another question. It's kind of curiosity, but because I mean, if this J turns out to be all antiferromagnetic, so in principle you get some sort of frustration in your system. So I wonder if we do this long range, and how this actually can play out with coherence. I mean, depend on the sign of this long range Dij. I mean, depending on how they decay on space.
Okay, so first of all, why is it nearest neighbor? I mean, the exchange coupling is really very local because it really is based on nearest neighbor tunneling. I think, okay, you could, I mean, maybe what you're saying is that in principle, you could have next to nearest neighbor tunneling. I think this is an extremely small effect. So, and also maybe I should say that if you don't want this tunneling to happen, you can always switch it off with this barrier, right? So what you will do here is all the barriers between quantum dots are basically high, and then you decide to couple, spin 1 and spin 2, and then you lower this particular barrier, and then these two will couple. I mean, there is, in addition, of course, there is also there is also the magnetic dipole interaction between the spins, which is a bit more long range. But I think this is also very, very weak. I think it's negligible, actually. And now, I mean, this also, I think, probably answers your question about frustration. I mean, in this J here, indeed, it can be negative, or it's I think typically it is antiferromagnetic. But again, because most of the time these spins are uncoupled, and you only couple them pairwise and not, I mean, you would not couple, let's say, several in a row at the same time. I think this frustration typically doesn't occur. So this would only happen, let's say, if you have a chain that has, let's say, a loop in it, and also you would switch on the exchange between all of them at the same time. And I mean, you can do that, but you don't have to. And for quantum computing, you would probably not do it.
Yeah, because I was just wondering the last part of your talk when you'd like to have this long range Dij. So I was just wondering how this.
For the long range, okay. So for the long range, of course, then what you want basically is that you can really choose two electrons and only couple those to the resonator at the same time, and then the others are uncoupled. At least for the quantum gate, right? That's what you want. You may ask, can you then do gates in parallel and so on, and that's maybe not so easy. But of course, let's say if you forget about quantum computing and you're just interested in coupling all these spins, I mean, you could have an interesting coupling of all the spins to one cavity mode, and you can switch them on. I mean, you can switch all the couplings on at the same time. And then you get an interesting model. I mean, you could get this, I think basically this would be a Dickey model. And these have interesting behavior. Even you could even see maybe some phase transitions. It could be interesting, but it would probably not be what you would do for long-range coupling between qubits.
Okay, it's clear. So thanks. Now I understand better.
Okay, great.
Thank you very much for that. So now I have a question from Carlos. So he's thanking you for this very nice talk, and he's asking your view on the Majorana qubit or topological quantum computing, and he's asking, are they still in the Stone Age phase? And if you think in your opinion, they are a competing platform for quantum computing.
I think, thanks, Carlos, for this great question. This is, of course, a nice, I think it's a nice opportunity for me to to say something about. I mean, I think Majoranas are very interesting, but I think they're not even in the Stone Age because they don't have a qubit. You know, I think in gallium arsenide we did have a qubit. It was not very good, but I think the Majorana is not even a qubit yet. We first have to see the qubit. So I think while it's interesting physics, I think what was before the Stone Age, I don't remember.
Okay, so thanks for the clarification. So I guess I don't know, Carlos.
I think maybe if I can add to that, I think they're trying to go. They're trying to skip. They're trying to skip the Stone Age, the Bronze Age, and the Iron Age. Or they directly want to go to the I don't know, maybe Iron Age.
Okay, I guess Carlos wants to make some comment.
No, I just wanted to say that, yeah, well, I was just provoking. I noticed you carefully avoided the M word. Right? But it's interesting because, you know, depending on who you talk to, they probably will claim there is a qubit, right? But this is still up on some kind of controversy.
And I think in theory, there's a qubit, but I think experimentally, I'm not so convinced that there's even a qubit. Yeah. I mean, a qubit means that you have a well-defined two-level system which lives long enough so that you can do coherent operations. And I mean, let's say you see a Rabi oscillation.
So, but Guido, let me ask you, because this is a colloquium for our students. Most of them are undergraduate students. Perhaps it's a good chance for you to say something about how important it is, you know, to learn, specifically in this area, quantum mechanics, and how important. You already mentioned that, you know, even in the case of the Majorana, and that's certainly my opinion, that quantum computing as a whole, and you know, this started, I don't know, some 20 years ago or so, even more than that. Despite whether or not they're going to be delivered at some point, what we already learned about quantum mechanics and how quantum mechanics became sort of a, you know, an everyday kind of thing, closer to an everyday kind of thing, you know, is really interesting to see. I mean, people thinking about, you know, entanglement and all kinds of concepts that, you know, at my age, I'm, you know, a bit older than you, you know, when we learned quantum mechanics, everything was like, you know, dogma, you know, and now there's some things that people are doing in labs. So could you say some things about, and of course you and I you know, work a bit with you more than I, closer to experimentalists, high level experimentalists, also in this topological stuff as I'm involved. And so this interplay between theory and experiments seems to be very, very important. So could you comment and mention and try to motivate our students in this regard?
Yeah, sure. I mean, I think you're right. I mean, I think first of all, I would say that quantum mechanics is absolutely essential. It's really the basics for all of this, and of course for much more. So whether or not quantum computers will eventually be realized to an extent that we can use them for problems that we really care about, I don't know, maybe, but I think there are of course many applications of quantum mechanics, and I mean this quantum mechanics is really the basics. And what I can see at the moment is that even there's a wide kind of need for scientists and beyond physics, so also in engineering, because this is really growing, this quantum technology. I mean, you know, quantum technology is really going beyond quantum computing. Of course, there are of course already applications where I'm very optimistic. Let's say quantum sensing, quantum communication. These are areas where basically there are already applications that are working, and for all of these, quantum mechanics is really the absolute basics. So I think if you know quantum mechanics, you're a very, I mean, this is a very sought after skill nowadays, and I think both in academia and industry, I think it's really important to understand it. And as a physicist, you have, of course, we have a big advantage because we have this opportunity to understand what's going on. And so I don't remember what the second question was, but I think so. I think I would encourage everybody that to really invest in learning quantum mechanics. And then, I mean, you also mentioned the interplay between theory and experiment, and maybe that's a bit more personal. I think different people working in theoretical physics, let's say, they have different tastes and attitudes. I think for me, it's been, I mean, I like doing pure theory, where we basically do something and then we just see how people accept it, and we don't care what people do whether people immediately measure it. But what I also really appreciate and enjoy is to collaborate with experimentalists. And it's, I mean, it's very interesting, and I don't know, it's very exciting, this two-way collaboration where on the one hand we can propose something. So I mean, I can show you an example. I mean, this I showed it maybe briefly. When so basically we were working on this gate. I mean, we really came up with this idea, and something like this was done in NMR already earlier. But basically, we basically had this scheme, and in this case, I showed it to Jason Petta, and then they said, okay, they're going to realize it, and they did it, and it works. So, and I think that's really a nice, it's a nice kind of interaction, and of course it also goes the other way, that they show us their results, and then we can build up theory. And then Carlos, I'm sure you know this, but just to say it for maybe students, I think for me personally, this is a great thing, and it's a great way to make progress. And I think in physics, I think many of the important results have somehow emerged in this way, that there was either an experiment that was unexplained or a theory that wasn't tested. So maybe there are also theories that are just theories for a long time, and then at some point they were measured, and that's it. But yeah, I think I enjoy it. It's very nice.
So thanks, Guido, for the nice talk and the very detailed response for this question, and explain to the student the importance of quantum mechanics. So I see no further questions here in the chat. So I'd like then to thank you again for presenting colloquium for today. It was really nice. So, and I expect to see you back in São Carlos someday in person. So whenever this crisis.
Yeah, I would enjoy that, and it would be nice to see some of you in Konstanz at some point. Yeah. Thanks a lot for having me. It was a great pleasure.
Well, that was our pleasure. So I thank everyone which was watching YouTube. So thank you so much. And then we'll be back on November the 13th. So then we'll have a talk about the ice cube neutrino experiment. And then I see you then. So bye-bye.